Welcome, everybody. This is the third of 4 webinars looking at the results from the National Survey of Attitudes of Wind Power Project Neighbors. Today we are going to be talking about predicting audibility of and annoyance to wind power project sounds using modeled sound. I am joined today by 3 exceptional individuals. Ryan Hack, who is a Senior Acoustic Analyst at RSG, along with his colleague Ken Kaliski, who's the Senior Director, and Matt Landis, who's a Data Scientist there. As shown here on the first slide, everybody is in muted mode for this webinar. We have over 100 attendees, and so we encourage you, though, to submit questions via the chat window. We'd like to hear from you. And you can do so at any time during the presentation. We will be monitoring it, and we will give ourselves time at the end to go through the questions. As you might have heard just a moment ago, the webinar will be recorded and will be stored on our website for you or others to watch the webinar after today. We will also be storing these slides that you'll see today on the website after the webinar as well. So, why don't we get started? About RSG, you can see here, this is very nice pictures of Ken, Ryan, and Matt. I'm going to leave this slide in here for folks to look at this in great detail, but I just want to point out that it's been an exceptional pleasure to work with these individuals. This is a different area that our lab is not particularly skilled at, and so to bring in folks as talented as Ken, Matt, and Ryan has been a real pleasure and added a great deal to the research, as we'll talk about today. The plan is for me to give a little background at the beginning, and then I'm going to hand it over to them to cover part 3, and then they'll turn it back over to me to just talk about a slide or 2 about next steps and outreach, and then we'll open it up to questions and answers. So first, a little background on this project. The National Survey of Attitudes of Wind Power Project Neighbors is a multifaceted project. As most of you know, if you've participated in the webinars to date, it's a collaboration of a variety of individuals from a variety of institutions, each bringing in their own skill sets to lead areas of the work. And I hope you get a chance to look at and listen to the past webinars if you've not done so already, which highlight some of those individuals, and as will the final webinar that will be conducted in 2 weeks by the folks from Martin Luther University. So why study wind power project public acceptance at all? Well, these slides exhibit one area that might help understand why this is an important aspect. The slide on the left discusses and shows the numbers of individuals living within close proximity of the U.S. turbine fleet as of 2015. There were approximately 1.4 million homes that were within 5 miles of turbines at that point. Now, of course, since 2015, additional turbines have been installed in the United States, and those numbers continue to grow. On the right side, you see a figure showing the average distance to the nearest homes from each of those facilities and from turbines in those facilities. And you can see that over time, those distances have been creeping down. So that we have kind of a growing trend here where communities that are surrounding wind energy facilities are both growing in number and becoming ever more apparent of those turbines. A third thing to think about is the fact that turbines themselves have gotten much larger over time. And so therefore, they're much more omnipresent in the environment around these communities. This means that individuals are obviously impacted a great deal, whether it's visually or potentially auditorily by the presence of those facilities. As well, communities that are considering wind energy often hold the keys to whether permits are whether the project can be accepted in the community and is allowed to be built. And so this is sort of another reason why communities can play such a big role. And so it's really important to understand how they are reacting to the facilities that have been built to date so we can better understand what are going to be likely impacts, both positive and negative, for projects built in the future. Now this talked about basically the same things that I just talked about on the previous slide. The only thing I'd like to point out is the last bullet here, which is one of the areas that we see this work covering is allowing the stakeholders and the DOE to better understand what priorities they should use to increase the benefits and reduce the costs of the next generation of wind technologies and deployments. This project spans now 4 years. It started with a literature review and then collected data, conducted analysis, and we are just finishing up analysis as we start to prepare the deliverables, which today is one of, and conduct outreach. No surprise there, this is sort of a normal process for a research like this to conduct. And in the next slide, I'll talk a little bit about the literature review, and then we'll focus on the results that are part of the analysis. So the literature review we conducted at the beginning, this work has been published. It was led by my colleague Joe Rand, and it was a great piece of work because it allowed us to really understand what that North American literature was telling us and how to fit our research within it. The literature review is quite long, and I'm obviously not going to be able to discuss it today in great detail, but this gives you some sense of some of the research gaps that we identified by looking at the North American literature and also the literature that had been conducted simultaneously in Europe. One of the main areas that focuses on this presentation today that we did not see covered in the literature is the ability to correlate attitudes and annoyances to modeled or measured sound. And that is the focus of our presentation today. So I'm going to talk now about the survey frame, giving you a feel for the data collection effort and the data that we collected. So the survey is a multimodal survey that was conducted starting in late 2015, but mostly in 2016. And by multimodal, I mean we collected data via the phone, the internet, and the mail. And this allowed us to try to capture a broad set of the population so that we know that our responses are representative of the underlying population. The survey is quite long. It's 22 minutes with over 50 questions. And we ultimately ended up with 1,705 valid responses, which is a 22% response rate. Now, we actually felt like this was quite good given the fact that we were collecting data at the same time the election was occurring, and most people were being inundated with calls for various reasons having to do with that. The responses were collected near 250 wind power projects across 24 states, and they're shown here on the map in the green dots. I also want to bring your attention to the red stars. Those are wind projects around which we modeled the sound, and that will be the focus of the presentation today. Every one of the facilities that are depicted on the map are what we consider modern wind facilities, which are greater. The turbines are greater than 364 feet tall, and they are greater than or equal to 1.5 megawatts. The respondents from our survey were all within 5 miles, but we oversampled close to the turbines, and we wanted to do this to make sure we captured that particular cohort that otherwise is pretty difficult to reach. If you just sort of randomly sample around wind facilities, you'll tend to get people that are much further away. But we wanted to make sure we heard from those individuals that were living quite close to the turbines. This is especially important for the presentation today when we're looking at modeled sound, where sounds from the turbines obviously don't emanate out to broad distances many miles away very easily, but they would obviously be apparent to those individuals living quite close. We also oversampled near large projects because for the same reasons, if you just randomly sample, you'll tend to sample near relatively small projects that are installed in relatively densely populated areas. And finally, as will be the focus today, we oversampled where sound was modeled. We wanted to make sure we got as many respondents as we could near those facilities. The distribution of responses is shown here on this slide. Most respondents are quite close to the turbines, as we said, And those individuals, that distribution is in fact opposite of what would normally be expected given the distribution of a population. And so to correct for that, we needed to weight the population, and we did so not only to adjust for the sampling distribution, but as well to correct for differences in our sample and the underlying population, such as the average gender of the underlying population and that of our survey, and the age and the education. So all the responses and the results you'll see today are weighted. The analysis areas that I mentioned originally that we have that covered this research are listed on this slide. We today are obviously focusing on the third bullet under the topic specific analysis areas, predicting audibility of and annoyance to wind project sounds. And I'm just about to hand it back over to Ken and Matt and Ryan, but before I do, I wanted to just note that these are preliminary results. These results have not been submitted to nor reviewed by reviewers for a peer-reviewed journal. We expect that to occur over the next few months, but you should know that they could change over time either during that process or prior to it. That notwithstanding, we encourage you to cite the results if you wish to. You'll have this PowerPoint slide deck available on the website, and we've given you a citation here, which is obviously will be part of the deck. But I wanted to note that these are preliminary and therefore could change over time. So with that, I think we are ready to hand it back over to the RSG group. Let me introduce, I guess, Ryan or Ken, who's going to take it from here.
All right, Ken. Yeah, thank you, Ben. So this part of the presentation is predicting audibility of and annoyance to wind power project sounds using modeled sound. And there we go. Oops. Everyone went too far. So I just want to acknowledge the other collaborating, contributing researchers. More specifically, we're going to be investigating various predictors of the reported ability to hear turbines, that is audibility, and stated sound annoyance from wind turbine sound. And this is a subset of the 1,705 total respondents, it's 651 respondents, where we modeled sound levels. So the presentation is 4 basic parts. The first is talking about sound levels and the survey data summary. I'll just give you an overview of some of the levels and metrics that we're using, and then turn it over to Ryan to talk about audibility and annoyance, and then more specifically audibility and annoyance inside the home, and then to Matt to discuss the predictors of sound annoyance using modeling. And then I'll conclude with our initial takeaways and what we're doing for future work. So the sound levels that we're going to discuss today are A-weighted. And to help you understand that, I just put in 2 charts here. On the horizontal axis on the bottom is a frequency, and it ranges here from 10 to about 20,000 hertz. The nominal audible range for humans is from about 20 hertz to 20,000 hertz. And this chart on the vertical axis shows essentially the sensitivity of the human ear. And we can see that our human ear is very insensitive to low frequency sounds and much more sensitive to mid and higher frequency sounds. And so we use this A weighting on the right side to essentially mimic that human sensitivity of sound at these lower and moderate levels that wind turbine sounds occur in. When we're talking about sound levels, we're going to be talking about sound levels from the turbine or the turbines, and that's obtained through sound propagation modeling. And then we're also going to talk about background sound levels, that is, without the turbines. So the sound propagation modeling is done using the international standard ISO 9613-2, and we're using mixed ground or mixed ground hardness, a mixture of soft and hard ground, and adding 2 decibels. And that's intended to simulate a 1-hour maximum equivalent average sound pressure level. We calculated those sound levels for all the 651 respondents, and those account for 31 different wind turbine developments. We also estimated for each of those the background sound level, and that is the estimated daytime median sound level, or L50, using the National Park Service's geospatial sound modeling model that you can obtain from the Park Service, and we have the reference down here. So I'm going to turn it over to Ryan now, and he's going to talk more about the results, starting with wind turbine audibility.
All right. Thanks a lot, Ken. This is Ryan Hawk. Ben, get it ready to pay the price. So here we are. I'm just going to dive right into the data, and we're going to talk about what kind of conclusions we can draw from these responses that we observed in the data set. So what we're showing here are the respondents in our data set grouped by distance, from closest to the turbines here at the bottom to farthest away from the turbines here at the top. The colors represent the reported audibility of each respondent. So the lightest color being those who reported not being able to hear the turbines. Those who could hear them on their property is the orange, and the red denotes those who reported hearing the turbines in their homes. So back to the bars over here. One thing I want to point out is that really above 1 mile, there's very little audibility of wind turbines. People cannot, for the most part, hear wind turbines on their property outside of 1 mile from the nearest wind turbine. But once we get within a mile is where the data start to get interesting. And so with that, I want to draw your attention to these pie charts here that look at the proportions of the population represented by the sample and how that's distributed across distances. So once again, outside of 1 mile, almost all respondents, or almost all people in the population, cannot hear the wind turbines. Both inside of 1 mile, specifically between 1/2 mile and 1 mile from the nearest turbine, about 40% of the population can hear wind turbines on their property. And about half of those, or 20% of those between 1/2 mile and 1 mile, can hear wind turbines in their home. Then moving closer to those who live within 1/2 mile of the nearest wind turbine, 75% of them can hear wind turbines on their property, and 50% of those living within 1/2 mile can hear a wind turbine in their home. So now, attaching some sound levels to these audibility levels, I'm going to spend some time here describing this plot, because you're going to see the same plot several times, or at least the same layout. So what we have here on the y-axis is respondent audibility level from at the bottom, those who cannot hear, to those who can hear it on their property, to those who can hear turbines in their home. And on the x-axis here we have model wind turbine sound level that we produced from the sound propagation modeling from 0 to just above 50 dBA. And each dot on the plot represents a respondent, and they're placed in their appropriate audibility level that was reported. And we also show the cat and whiskers or box plot that kind of that shows the distribution of sound levels within each audibility level. And of course, the center line of that box plot is the median, and the little red star here is the mean or average value of the sound level of that within this each audibility level. So what can we take away from this plot? The first thing to notice is that on average, those who cannot hear have a lower model wind turbine sound level at their property, and this is logical. But one thing that we can note is that there's a lot of distribution. There are very low sound levels, which we'd expect, but there's also some really high wind turbine sound levels of some people that cannot hear. So that's one thing we need to explore. But then as effectively as wind turbine sound level moves up, more people are likely to hear the turbines either in their homes or on their properties. So what we do from here is then now look at the same distributions, but now with background sound level here on the x-axis. And so one thing we can see here is that on average, with a higher background sound level, people are more likely to not be able to hear the turbines, and maybe with a lower background sound level that they may hear it. But you'll notice, again, there's a great deal of variability or distribution across sound levels. And so one thing we suspected was that these two quantities, both model wind turbine sound level and local background sound level, somehow interacted to describe audibility. So here's where we start to talk about that interaction. And so what we're showing here on this plot is the same y-axis from those who cannot hear to those who can hear turbines on their property to those who can hear it in their home, and the x-axis is the modeled turbine sound level. And then what we've done is we've broken up the background sound levels into categories or ranges from over here, the red line being those at the lowest background sound levels to the purple line being those at the highest. And so what we see is that as sound level increases, one thing I should also explain is that now we're showing these lines. These lines are basically trend lines that have been fitted to the data to kind of give us an idea of the trends seen in the data. So with that, what we can notice is that really irrespective of background sound level, audibility does indeed increase as wind turbine sound level also increases. However, at this lowest sound level category, those with background sound levels between 30 and 35 dBA, will likely hear the turbines at lower modeled sound levels than others. The respondents grouped here between 35 dBA and 50 dBA essentially have very similar audibility patterns in regard to modeled turbine sound levels. And I'll also note here that at 50 dBA and above, which would represent a more urban area, we did not have any respondents that reported hearing the turbines, and one reason for that is that the maximum modeled level we had for one of those respondents was about 42 dBA. So with this, there's still something we're missing in this plot to really explain audibility, and so that's where we now introduce a new quantity called sound level difference. And this is going to take a moment to explain, but essentially we have the same y-axis, and now the x-axis is this quantity called sound level difference, or maybe relative sound level. But what sound level difference is taking the modeled turbine level and subtracting the background to basically give us the relative level of the turbines and background. And so a sound level difference of 0 represents a respondent where the modeled turbine sound level is the same as the background. And similarly, for a positive sound level difference, this would be where the wind turbine sound is higher than the background sound levels. So how I'm going to explain this plot is with an example. So again, taking the sound level difference of 0, and we look at still these same background sound level categories with depicted by the different colored lines from red to purple. The red being those who experience the lowest background sound levels in their community. We see that with a sound level difference of 0, so the same model wind turbine level as background, that they're likely to either not hear the turbine or only be able to hear wind turbines on their property. Whereas going all the way up to this blue line, being those with background sound levels between 45 and 50 dBA, with a sound level difference of 0, these people are likely to hear the turbines on their property and potentially in their home. So why this is important is that the background sound level category between 45 and 50 dBA, to have a sound level difference of 0, that means the modeled wind turbine level is between 45 and 50 dBA. Similarly down here for the lower background sound levels, to have a sound level difference of 0 and be in this category of 30 to 35 dBA background, they have to have a modeled turbine sound level of between 30 and 35. So what this tells us is essentially that audibility is dependent on the modeled wind turbine sound levels and best contextualized by background sound level. Give you a moment to digest that. So, some takeaways regarding audibility. Wind turbine audibility increases with turbine sound level, and we also suspect that local background sound masks wind turbine sounds. And what we just talked about, that at higher background sound levels, respondents could hear turbines at smaller sound level differences, indicating that its audibility is really dependent on modeled sound level of the turbine, or not necessarily modeled, but sound level of the turbine, period. So now moving on to discussing noise annoyance. So sorry for the busy slide, but let's just start by going over the questions and how we formed our data set. So starting with question 22 here at the top, have you ever heard sound from the wind project? They could have answered yes, no, or don't know. So if they answered yes, then they proceeded to answer the question, can you hear sound from the wind project when you are on your property but outside your home? If they answered yes to that, then they reported some level of annoyance to sound of the wind project, from not at all annoyed, slightly annoyed, somewhat annoyed, moderately annoyed, or very annoyed by the wind turbine sound. If the respondents answered no to either of these questions, that they have not heard a wind sound from a wind project, or they cannot hear it on their property, they were put into this other group, which we'll call the cannot hear group. And so one thing you'll notice is that about half of our respondents could not hear the wind turbines, and about half were able to hear the turbines on their property and reported some level of annoyance. To look at this, or to study this, we simplified the annoyance categories in essentially combining these middle three, slightly, somewhat, moderately annoyed to become mildly annoyed, leaving us with four categories. The first being those who cannot hear, then respondents who could hear the turbines on their property but were not at all annoyed, then those who could hear the turbines on their property and were mildly annoyed, and then, of course, those who could hear the turbines on their property and reported being very annoyed by the wind turbine sound. So now, looking at a similar distribution as we looked at with audibility, you'll notice this plot looks very similar. But what's changed now is we have four groups now. We have those who cannot hear, being the lightest color, and then getting darker, those who are not at all annoyed, those who are mildly annoyed, the orange, and the red is those who are very annoyed. Going back to these bars that are broken up by distance to the nearest turbine, once again, there's very little audibility and annoyance outside of 1 mile. But then once we get within a mile to the nearest turbine, that's when we start to really get into the analysis that we're concerned about. So trying to draw some conclusions from the population proportion of people who are annoyed, once again, outside 1 mile, most people cannot hear the wind turbines and are therefore not annoyed by the sound. But then between a half mile and a mile, about 75% of people still express no annoyance to the wind turbine noise. 20% of them between a half mile and 1 mile were mildly annoyed, and very few were very annoyed. But then coming down into those who live closest to the nearest wind turbine, within a half mile, 20% of that population was very annoyed by wind turbine sound. It's also interesting to note that about the same percentage, 20%, of respondents between a half mile and a mile, and those less than a half a mile, that's about the same proportion of those who are mildly annoyed. So really what's changing, I didn't want to do that. But what's changing is this, the proportion of those that are very annoyed, and those who live closest to turbines are those reporting the most annoyance to sound from the turbines. So now looking again at sound levels on the y-axis, this time we go from, we have respondent annoyance level, and we go from those who cannot hear to those who can hear it but reported being not at all annoyed, those are mildly annoyed, and those are very annoyed by the wind turbine sound. And so we see a pretty similar trend, but maybe a little less defined as what we saw with audibility. First, it's clear that on average, those who cannot hear, they have lower modeled wind turbine sound levels than those that can. However, when we look at between these three groups of not annoyed, mildly annoyed, and very annoyed for modeled wind turbine sound, there's not much difference in the means and medians and the distribution even between these groups. I suppose the distribution of very annoyed is smaller. They're grouped together closer. The sound levels, that is. Sorry. So then moving on to background sound levels, we see that those who reported not being able to hear the turbines or could hear them and were not at all annoyed, on average they had higher background sound levels than those who were mildly annoyed or very annoyed. But once again, we suspect there's some sort of interaction between model wind turbine sound levels and the local background sound levels. So here we go with the interaction. Now what we're showing here is once again from cannot hear the turbines on their property to those who could but were not annoyed, mildly annoyed, or very annoyed. Once again grouped by background sound level category, and on the x-axis is modeled wind turbine sound level. So what we see is that at the lowest background sound levels, respondents are getting more annoyed at lower modeled wind turbine sound levels, at lower wind turbine sound levels. And similarly at higher background sound levels, it's taking, or respondents are less annoyed at similar levels. For instance, looking at this 40 dBA line where the quieter backgrounds, may be annoyed, but likely down here with the higher background sound level, this blue line, they probably cannot hear it or may not be annoyed. So essentially what we're seeing here is that in the absence of controlling variables, so only looking at sound levels in regard to audibility and annoyance, lower background sound levels lead to more annoyance at similar modeled sound levels. Now, for the rest of the presentation, really, we just want to concentrate on those who reported being able to hear the turbines and reported annoyance. And so now our new data set is essentially half of what we were dealing with before, and about half of this new data set is not at all annoyed. And so with that, we're going to go back to that interaction that we showed, but we're going to exclude the people who cannot hear it. So once again, we're only looking at people who can hear the turbines and who reported annoyance, some level of annoyance, which could be not at all annoyed. And so with that, what we see is that there's essentially no clear trend between wind turbine noise annoyance and A-weighted sound levels among those who can hear the turbines. The sound level interaction breaks down, and really there's no sense essentially these lines, these trends don't make sense, and sound levels are all over the place. And really what we want to take away from this is that that there is no trend. Once we only consider those who can hear the turbine, that sound levels aren't really describing annoyance very well. So some takeaways in regards to annoyance. Wind turbine annoyance and audibility increases with sound level. Higher background sound levels mask the turbines and thus produce less audibility and annoyance. And that when only looking at respondents who could hear the turbines on their property, wind turbine sound levels alone do not exhibit a clear trend to determine one's annoyance level. There we are. So trying to bring these two together now, we're gonna look at some more results that combine audibility and annoyance, and particularly look at where people could hear wind turbines and how that affected their annoyance. So what we've done here is we've grouped those who can hear the wind turbines up here in this top bar, those who can hear wind turbines in their home, and then in the bottom, these are people that can hear wind turbines from their property but not in their home. And then we have the same color scheme with those who are not at all annoyed in the lightest color, and the orange is mildly, and the red is very annoyed to the wind turbine sound. And so there's a couple things I'd like to point out here. First is that those who reported only being able to hear turbines from their property but not in their home, very few of them were very annoyed. Most of these people were not annoyed, and some, almost a third, were mildly annoyed. But then once we get up to those who can hear it in their home, what we see is that almost all of these this red group, the very annoyed group, almost all of them can hear the turbine in their property, can hear the turbine in their home. But similarly, those who can hear the turbine in their home, it's just about evenly distributed between very annoyed, mildly annoyed, and not at all annoyed, which is shown over here very well in this pie chart. So essentially a third of those who can hear the turbine in their home were very annoyed, a third of those who could hear it in their home were mildly annoyed, and a third of those who could hear it in their home were not at all annoyed. So to try to summarize that again, so almost all very annoyed respondents could hear the wind turbines in their home. Respondents who could hear the wind turbines in their home were distributed evenly amongst the annoyance levels, and about 1/3 of those who could hear the turbines on their property reported being mildly annoyed, and most others were not at all annoyed. So with that, I'd like to turn it over to Matt Landis to talk about the regression models that we developed.
Thanks, Ryan. So the point of the regression models is to take into account additional factors that we think are important, and look at them all together look at them with the sound levels and put them into a larger context of the other things that might affect people's reaction to the sound levels. So I'm going to talk a little bit about the regression models themselves, and these are all what are known as ordinal logistic regression models. We talk about how we decided how well the models worked, and then the results of the models. And then I'll hand it back to Ken to bring us home. So we really used 3 separate regression models to look at how well we could predict respondents' levels of annoyance. And the first model is just including the sound levels that Ryan was talking about. So the sound levels of the wind turbines and the background sound levels. And those are the only 2 factors that we had in the model. Then, in addition, the next model that we tried incorporates those 2 variables and adds 3 more. And these are things that are observable. We're calling it the objective model. So because these things are all directly observable, can the respondent see the turbine from their property? Did they live in the area prior to the wind turbine development, or did they move in afterwards? Are they hosting a wind turbine on their property, or are they receiving compensation for the wind turbine, or not? And then the third model incorporates all of those things and adds 2 more variables. And these are things that are subjective, like more of like how people feel about wind turbines and the noise. So the 2 things that we added in there were prior to the project being built, did you support or oppose the project? And obviously has a lot to do with how they feel about wind turbines, wind projects in general. And then also, did they respond that they were sensitive to noise, yes or no? So, and we also included some basic demographic variables like age and gender and things like that, and stratification variables that were included in the regressions to account for the weighting. So I also want to talk a little bit before we show the results about how we decided how well the models were working. And we used a procedure called leave one out cross-validation. And the basic idea here is that we take the data set and we, one by one, we drop each respondent from the data set, and then excluding that respondent, we fit the model and then use the model to predict the response of that person. So we're trying to, and so then we do that for every respondent in the data set, and then we calculate the proportion of answers that we were able to correctly predict. And that's what we're showing over here as an example. So here's people who said they were not annoyed, mildly annoyed, or very annoyed, and then what proportion of those did we get correct? And the ones that we got correct are in this green box here, and then these were incorrectly predicted. So it's so if we did everything, if our model worked perfectly, we would expect to see something like this. And of course, that's not what we see because there's a lot of variability in people's annoyance in response to these questions that we can't take into account, even with the number of variables that we have. But so this is how well our models performed. And you can see that for the models that included just sound levels, we're pretty good at predicting whether people were not annoyed, but that seems to be the default response for that particular model. And so it doesn't account for, it doesn't accurately predict levels of annoyance greater than that. And there, in fact, this model didn't predict anybody as being very annoyed. So sound levels alone are not sufficient. As Ryan was saying, sound levels alone are not going to be sufficient just to predict how annoyed people are with the sound of the wind turbines. So then if you add in the observable kinds of things, like whether or not they could see the turbines from their property or whether they lived there before the project was built, then we get a little bit better at predicting whether or not people are annoyed or not. And then finally, when we include how people feel about the sounds of wind turbines or how they feel about the projects themselves, then we get a lot better at predicting, especially predicting whether people are very annoyed. But you can see that we have about 58% correct prediction. So there's still a lot of things that we haven't incorporated in the model, and Ken will talk about some of those things at the end. So the next slide, I'm just going to summarize some of the results that we got from this particular model and how each of the variables that we included in that model rank relative to each other. So this is showing these are the predictors that were in the model, the responses to the questions or the characteristics of the person or their property, and they're in descending order of importance. And this is a measure of how statistically, how important they are in the model for predicting levels of annoyance. And you can see, and the ones up in between these dotted lines are the ones that were statistically significant. So those are we're only going to focus on those for this last part of the discussion. And you can see that the most important variable was how they felt about wind projects before they were built, and that's assuming that they lived there before the project was built and account for whether or not they moved in after. So this variable accounts for both of those things, and that's the most important factor predicting whether or not they were annoyed. But also the other subjective variable that we included was how sensitive are they to noise. So that makes some good intuitive sense. So noise does play a role for sure, and you can see that the third most important variable is the sound levels of the wind turbines. So how loud the wind turbines are once you account for the other things, that does seem to be important in combination with how sensitive they are and how they feel in general about these wind projects. And then to round out the significant variables, you can see that there's age is an important characteristic here, and the level of annoyance typically goes up to a certain point and then decreases again. That's what this quadratic term indicates. And then finally, whether or not you were if you were hosting a wind turbine or you're compensated for it, that generally meant that you are less likely to be annoyed with a wind turbine, as you might expect. So, so I'm going to turn it back over to Ken, and he can summarize things for us.
Thank you, Matt. So the main takeaways at this point are that within a half a mile of the nearest wind turbine, about 75% of the respondents reported hearing the wind turbines on their property, and half the respondents in this data set reported hearing wind turbines in their home. Almost all the very annoyed respondents could hear the wind turbines in their home, and about a third of the respondents who could hear the wind turbines in their home were very annoyed. The modeled turbine sound levels and local background sound level, essentially the median sound level, interacted to explain audibility, but less so annoyance. In fact, the A-weighted turbine sound level taken alone is correlated with audibility, but not annoyance. So when we combine subjective variables, objective variables, and the sound level variables, those provide the best insight into annoyance predictors. And we're able, using that model, to predict about 45% of the respondents that reported annoyance to wind turbine sound were successfully predicted by the regression model. But there's still unexplained variance, and especially in predicting those who are very annoyed, and that leads us into our future work to try to reduce that variance. So the next phase of the research is to increase the size of the respondents. As I mentioned, right now we have about 650 respondents out of 1,705. So we're going to try to increase that to over 1,000 by adding in 24 additional projects to model for a total of 55 wind projects. And then we're going to look at other characteristics of the projects that those people are around. So we'll look at the physical wind turbine and project characteristics, turbine capacity, capacity factor, hub height, RPM of the rotor, geographical regions, etc. And then we'll try to look at characteristics of the sound, for example, looking at the effect of low frequency dominance of the turbine spectra. And then we're going to essentially rebuild our regression model to try to better predict audibility and annoyance. And with that, I'm going to turn it back to Ben to discuss the next steps and outreach.
Great. Thank you very much. That's a really interesting presentation. I hope everyone on the phone enjoyed it. If you do have questions, ask them now. I can already tell we're not going to be able to get to the bottom of it, but we will be able to answer it. And I just checked in with the presenters. We are going to be able to stay a little late beyond the top of the hour to try to answer additional questions. We'll see how many we can get to. So this is just, I guess, the last slide, or second to last slide for me. Click on that, which is just to remind folks there is an upcoming webinar on March 13th that will dive into this area of annoyance a little differently, focused on those individuals that are annoyed and have symptoms that they attribute to the sounds of the turbines. And those results from here will be compared to results from other surveys conducted by our colleagues in Europe. So it would be a nice way to kind of compare and contrast. We are also be at the WEA Siting and Compliance Conference. For those of you that want to attend there, you can hear more about that. And ultimately, we will be submitting this work for journal publication and ultimately releasing the data and the survey instrument, hopefully by the end of the end of this year. Okay, so that's it. Let's talk about some questions. So I guess the process here, guys, is I will try to read through some of the questions and send them off to you. I think I answered what I could during the presentation for questions that I could answer, but many of these are for you. So let's see. I'm just going to start from the top. And the first question is about comparable studies looking at annoyance to other types of development within a half or 5 miles, basically within the range that we looked at it. Are you guys familiar with what sort of annoyances one tends to get around other types of development?
Now, Ben, I don't think that was a question asked in this survey. Is that correct? About whether they're annoyed by other sound. I think is that the question? Yeah,
no, I think this is looking outside of our work, but that's a good question. I can answer that. We didn't ask a question about other development. We did ask questions about how whether they found other sound emitting environmental aspects annoying, such as lawnmowers and, I can't remember them all now. So I guess what I'll do on that front is I will try to answer this to the questioner after the fact via email. But why don't you, if you have some sense as to other environmental sources of noise, such as other developments, maybe airports or industrial activities, which we did not ask about, maybe you can provide them some context there.
Right. So I think the questioner is asking sort of about dose response curves and how wind turbines compare to other projects. And in the context of this research, we haven't yet done a dose response curve or a comparison to other types of environmental noise. Part of the reason why we haven't done it yet is because looking at just turbine sound levels doesn't give us a very good statistically significant correlation with annoyance. But I think in the future work we should probably address that, but we haven't done it at this point.
Great. So next question is talking about some of the mentioned that these were relatively high Lmax values from wind turbines, and they asked how close to a dwelling how close were the dwellings when the levels were exceeding 50 dBA?
I don't know that answer. It'll be different for different projects. The sound level and the distance are somewhat correlated, but for a large project with a lot of wind turbines, you can get a smaller distance, but if there's only a larger distance, if there's only one wind turbine and you're 50 decibels, you're probably a lot closer. So there's no one answer to that question, but I guess in the future we could look at the relationship between distance and sound levels, but it's going to be a little bit sloppy because of that variability.
Yeah, that's a good point, that this model that doesn't just focus on distance, but focuses on all the other turbines and their distances as well, plus the underlying terrain. Okay, I'm going to jump to a different questioner here because one individual asked 5 questions in a row, so I'm going to just move on here. Maybe we can circle back, which is, do we have any survey questions asking respondents to describe the noise that is annoying to them? And I can answer that one. We do have additional questions talking about describing the noises, and we also have questions describing the frequency of annoyance. And those are not, we did not describe them today. I don't believe we have them in our summary statistics or supplemental slides today, but maybe we could add them, or separately I can get back to you via email to answer those directly. Next question is about wind turbine sound being directional, and if you considered the location of the home in relation to the turbine and I guess the more common direction of the wind.
Yeah, so we looked at prevailing wind direction and adjustments for wind direction to try to get into more about an exposure metric. And we didn't find a big difference, and that's why we're sort of focusing on the LMAX. We'll report those analyses as well when we do the report, but we did try to figure out different ways to look at exposure, not just essentially modeling a 1 hour maximum sound level, but looking at wind speed, frequency over the course of the year, and directionality.
Great, thanks, Ken. Let's see here. Can you tell us a little bit more about the rationale for choosing the measure 1 hour max when previous studies have used LDEN, LDEN, LDN, and L95, etc.?
Yes. So in the U.S., the 1 hour LEQ or some type of short-term LEQ metric is most commonly used for compliance. So that's where we're focusing on our studies. Again, I talked about some type, looking at more of an annualized metric. LDEN is the day, evening, night average level over the course of the year. LDN, the day-night average sound level over the course of the year. And those are a lot harder to actually calculate for all of these receivers because they're dependent on, again, weather over 87, 60 hours of the year, wind direction, wind speed, turbine output, etc. So for the use in the U.S., we're really focusing on something that's more of a common metric used in compliance studies. That said, however, we could try to, thinking we could try to adjust these to LDEN. There's a paper by Isaac Old, forget where is it, NorthCon, that looks at trying to commonalize, if that's a word, the metrics used in the various dose response studies because they are very different. Health Canada, the Pedersen studies, et cetera, they use different metrics. So this is a way of, so his paper was on trying to see what those dose response curves look like using the same metric. And I think he used something very similar, 1 hour or G equals 0.5 plus 0, I believe is the metric that he settled on. But anyway, you can review that paper, and if you need to get the reference or the citation, you can email me.
Great. I have a quick question here. Should be relatively easy to answer. How are the background levels determined? I'm going to see if I can jump to that particular slide here.
So the background level is determined using the National Park Service map. It's a 130-meter grid, I believe. 250-meter grid of the United States. And it's a machine learning algorithm that essentially correlates the sound level using their vast database of sound measurements to things like distance to roads and man-made objects and natural objects, and comes up with a median daytime sound level. They also, I think they've calculated other metrics, but this is the most relevant for our purposes. And if there's a website, see the website up here, you can find out more information about that model at that website.
Great, thanks, Ken. And we've reached, we just reached the top of the hour. So I wanted to give everybody an opportunity to disconnect, to thank everyone for joining today. We had great attendance. We are going to try to stick around at least maybe for the next 10 minutes, try to answer a few of the other questions. Again, I don't think we'll get to the bottom of them, but we will answer them via email. And again, this is going to be recorded if you want to check back. And I guess on the final slide, we had our email addresses. You're, of course, welcome to reach out to us directly via these email addresses. So with that, I'll let those that need to go. Thank you very much. And let's dive back into the questions here. So, question about the context that we are surveying individuals in their local community. Questioner wants to know, did we gather, I guess sort of take into account local and state regulated sound pressure levels at the sites surveyed? I can answer this, but Ken, maybe you can give it a little bit more context.
So
the quick answer is no. We aren't controlling for that. We've not collected data on that. But I guess I'd like to get your thoughts on how that could influence our results.
This is a question about whether we collected information about the standards that those were applied. They were applied to the projects.
Yep.
Yeah, we did not look at that, and not quite sure how we would it would be a difficult thing to look at, because we would also need to determine whether the individual property that we're modeling is a participant or a non-participant. So it would get very complicated. And then I'm not sure whether what the hypothesis would be about how that would affect annoyance. But it's something to think about.
Right. Here's a basic question. What was the height of the receptor used in the computer model?
4 meters.
4 meters, great. Okay, let's see here. Question about subjective variables. As we think about the next round of work, is it possible that other variables could be included in the model? For instance, something that was found to be statistically significant with attitudes, and also a very important aspect, which was the focus of our second webinar, is the perceptions of planning process fairness. Would you consider adding those variables, or a variable having to do with planning process fairness, into the regression as a subjective variable?
Oh, I guess the answer. Hi, this is Ryan. So yeah, we did consider using other variables, but we also kind of wanted to differentiate this analysis from the others involved in this work. For instance, that you've done, Ben, and Jeremy Firestone's analysis regarding planning process fairness. I can almost guarantee that would be very significant in the models. We also explained that we chose to use prior support and opposition because we felt it provided the best disconnect from someone's current attitude. If we looked at someone's current attitude and tried to compare that to annoyance, I mean, we're not really describing anything, because if they're annoyed, they probably have a very negative attitude towards the project. So the prior support and opposition was kind of the best disconnected way from someone's present self, let's say, that we had to be able to have a subjective metric like that. But yeah, I don't see why going forward we can't incorporate other applicable metrics like planning process fairness.
Great. All right, this is a question from Matt. Question about collinearity of the variables that were included in the regression. Did you check for that?
Yeah, I'm just trying to remember the details of that. We definitely looked for variables that were very highly correlated, or like, with correlation levels of like 0.8 or 0.9. And in those cases, we would pick one of the correlated variables and not include both of them. So we did check for that as part of the process for selecting which variables to include.
Hey, this is Ryan again. One specific thing I can say about that is that, as one might imagine, modeled turbine sound level and distance are very highly correlated. And for that reason, we did not use distance in these models presented.
Yeah. Thanks, Ryan.
Okay, so a question here about an earlier slide. I'm not sure, maybe one of you guys can move to that slide. I'm not sure exactly which one it is, but it says, can you advise the mean dB level at which turbines become audible at the property? It looks like it's just over 40 dB from one of the earlier slides. If you use you can use the little slider down below to move quickly between slides. And then you can jump to it by clicking on it twice.
Might be one of the box plot slides might show that.
Yeah, I guess one thing that we kind of talked about in the presentation was that it's really dependent on both of these things, especially for audibility. Right now, this slide's showing audibility and annoyance, but I mean, it's really dependent on that. What is the ambient sound level, at somebody's residence compared to what the turbine level is. That's going to really help determine audibility, and I can't answer that question with a specific number.
Right, that's a really good point. That seems to be something you sort of hit home today, is that you can't just take into account the modeled sound levels. You really need to look at the background sound levels if you're focusing on audibility, for sure. Okay. Will you be looking at whether the unexplained variance may be due to other individual factors in addition to noise sensitivity? So they don't mention other factors that we might look at, but I guess individual factors. I'm not sure we have more than the demographic variables to talk about there. We do have, as I mentioned earlier, whether folks found other sources of noise in the community annoying. Maybe that would be an example of other individual factors we could include in addition to noise sensitivity. Do you want to react to that question at all?
No. We'll be looking at. I think we'll just take another turn through it and see if there are other things. But I think the focus of the next step is to look at more objective variables around the turbine and the project characteristics.
Okay. Just a few minutes more here. I'm so sorry we're not going to be able to get to the bottom of these questions. Did you take, so this is a good question because I think it's easy to answer. If you'll move to maybe one of the regression slides at the end there that showed the AIC, the question was, did you get any information on the difference between people who get paid, compensated versus those that did not? And I guess I can try to move the slides quickly to there. So Matt, maybe that's a question for you. I'm just trying to figure out where we are here. I think it's this one.
Yeah, we're not showing the statistics that indicate the size of the impact, but oh, sorry, that's not the one I was.
So here I put this up because this is a supplemental slide that we included that is merely reporting on the survey responses. And one thing it's showing is that looking at someone, so host comp is essentially somebody who leased their property and was also compensated. Comp would just be someone who was compensated and did not host the turbine, and then no would be they weren't involved in any way. They may have been participating, but we don't know. But what this shows, just simply based on a distribution of the responses, is that all of those who hosted turbines and were compensated, none of them reported being very annoyed by the sound. However, those that were compensated reported being very annoyed at a similar proportion to those who had no relationship. Sorry, I thought I had the cursor, but that's what I'm talking about there.
Great, and those are in the supplemental slides. There's lots of slides in the supplemental slides, so you can't see them today except you did get to see this, but they'll be in the slide deck that are posted online. We encourage you guys to take a look at those. So that really gets us to 10 after. I think we need to stop it there. Really appreciate all the questions that have been asked today. I think we'll do our best, or we will do our best to try to give you answers to those. I don't know, there are about 16 or 17 more questions that we didn't have a chance to answer today. And we'll do that via email after the fact. And then as well, please feel free to reach out to us. So I guess with that, we will end the recording and end the webinar. And again, thank you for attending today. It's been a great pleasure.